Keep it on fleek, math geek. We're going to learn about Cauchy sequences. I'm sorry for saying on fleek. I'm better than that. Anyway, a sequence is called a Cauchy sequence. This is a new definition we're learning. It's something we can apply to sequences. If, for any epsilon, there is some index capital N so that for any two indices past that point, the distance between them is epsilon. So past a certain point, any two terms of the sequence are within epsilon distance of each other. Compare that to the definition of having a limit. If for any epsilon, which is positive, great, starts off the same. There is some index, capital N, great, continues the same, so that for any single index n past that point, the distance from xn to L is less than epsilon. That's the definition of having a limit. It's similar, but not exactly the same as being Cauchy. The definition of being Cauchy, I like to say, is an intrinsic definition. Look back to that top definition. If you have the sequence in front of you, what does it say? For any epsilon, past a certain point, two terms of the sequence are close to each other. Whereas the definition of having a limit is an extrinsic type of definition because you need to know this number L. You need to not only know what the sequence is, you need to know the number L so that you can say, numbers are close to L. So it relies on some external information, whereas the Cauchy definition only requires you to be able to compare terms of the sequence to one another, not to some third-party extra number that you have to figure out. Which makes it somewhat similar to our definition of lim_inf and lim_sup. Remember that the lim_inf and lim_sup of a sequence are the supremum of a sequence of infima, or conversely, the infimum of a sequence of suprema, which also did not require an external number. It was just born from the terms of the sequence itself. But finding those values is not necessarily easy, although we did show that they always exist. Okay, so here's a brief picture to represent the difference between these two definitions. So on the one hand, we have our original limit, that the limit as n tends to infinity of x sub n equals L. So you need to know what this value L is so that terms of the sequence are eventually trapped close to L. However, to be a Cauchy sequence, you don't need to know this extra number L. You just set epsilon at the beginning, and then you'd say past a certain point, so we have x sub 0 all the way up to x sub n, capital N. Forget about them, they're not going to matter. Past this point, any 2 points you pick are within epsilon of one another. Whether I pick these two terms of the sequence or whether I pick these two terms of the sequence, they're within epsilon. But if I picked this one and this one, they'll also be within epsilon of one another. So any two terms are within epsilon of each other, which means they're all bunched up pretty closely together. So there is a sort of cleanliness to it in that we don't need to know this extra number L. However, relating it to this external number L might be a nice grounded way to say whatever my sequence of numbers is, here's something it's like attached to. It is related to this number L. It's not free floating around in space. Now here is an important theorem. If a sequence converges to L for a real number L, not necessarily the limit being plus or minus infinity, but if it has a real number limit, then it's a Cauchy sequence. So the proof is I want to show that it's a Cauchy sequence. So I say let epsilon be positive. What we need to do is show that past a certain point, all terms of the sequence are within epsilon of one another. But if epsilon is positive, so is epsilon over 2. Standard trick. Since xn converges to L, past a certain point, all terms of the sequence are within half epsilon of L. Which means any two terms of the sequence can, instead of being compared to one another, can be compared to L. And through the triangle inequality, I get epsilon. So, two terms of the sequence, if I have this external limit, rather than comparing the terms to each other, I can say, let's just compare them both to L. And through the triangle inequality, this allows us to compare terms of the sequence to one another. And now, Lambo over there kind of has a clue that what's going to happen next. We showed converging sequences are Cauchy. And indeed, Cauchy sequences have limits. So if you know a sequence is a Cauchy sequence, it must have a real number that it is converging to. The proof is in 3 steps. First, we're going to show if the sequence is Cauchy, then it is bounded. Once we know it's a bounded sequence, the Bolzano-Weierstrass theorem says there's a subsequence which converges to something. And then we show that once this subsequence is converging to L, the original sequence is actually converging to the same number. So first we're going to show it's bounded, then we're going to say for free there is some subsequence converging to L, and then we're going to have to show that therefore the original sequence does as well. Why do we keep multiply defining things? This is sort of a theme. We define something, then we define something else, and then we show they're actually the same definition. They imply one another. They're logically equivalent. It's nice practice in forming proofs. Some of it is a bit of historical legacy. It wasn't immediately known that these things were equal or equivalent definitions. So perhaps person X defined what a limit is, and person B defined Cauchy sequences. Hint, that was probably Cauchy. Although I'm not a math history buff, so maybe he didn't actually attach his name to that definition. But whatever, there's 2 different definitions floating around, and after some time, it's able to be proved that they're actually the same definition. But both have been floating around, and both have sort of gained some acceptance. All right, step 1. Our goal overall is to show that Cauchy sequences converge. Remember, step 1 was to show a Cauchy sequence at least is bounded. So suppose xn is Cauchy, we want to show it's bounded. What we do know is that for any positive epsilon, just pick one, it doesn't really matter. Past a certain point, all terms are within epsilon of one another. We may as well let epsilon be 1, or 10, or 1,000. Any number will work, it just has to be positive. But past a certain point, all terms of the sequence are within epsilon of one another. Now, whatever that cutoff was, capital N, past which everything is within epsilon of one another, instead of comparing any 2 terms to each other, just compare everything to x sub capital N specifically. If little n is bigger than capital N, then the 2 n's are 2 indices that are at least as large as capital N, which means according to the definition of being a Cauchy sequence, the distance between these terms is no larger than epsilon. What that means is past capital N, all terms are no larger than x sub n plus epsilon and no smaller than x sub n minus epsilon, because every term has to be within epsilon of every other term, specifically that one, x sub capital N. So basically, what's going on is we've got our Cauchy sequence. Let epsilon be positive, i.e. epsilon equals 1. It really doesn't matter. Then there must exist a capital N so that if 2 indices are at least as large as capital N, then the distance between those 2 terms is no larger than 1. Now what we're going to do is not let M be something free-ranging. I'm just going to replace it with capital N. Capital N is bigger than or equal to capital N. So this means for any n past capital N, the distance from x variable n to x fixed index n is no larger than epsilon, which in this case was 1, which means all of these x sub little n's are in a fixed bounded range. So past a certain point, terms of the sequence are bounded. But what about before that point? Well, before that point, there's only finitely many terms of the sequence, and we know that finite sets are always bounded. So the sequence is bounded past a certain cutoff point because it's Cauchy, and it's bounded before a certain cutoff point because all finite sets are bounded. And therefore, the original sequence can be expressed as a union of the stuff before the Cauchy definition kicks in, and that's finitely many terms, and therefore bounded, and the stuff after the Cauchy definition kicks in, and that's bounded because we just showed it. And the union of 2 bounded sets is bounded, and therefore the sequence overall is bounded. Now, what Ethel is suggesting is that if the distance between terms is going to 0, that's sort of what the Cauchy definition suggests, but it's not exactly what it says, then of course the sequence is bounded. Yeah, Cauchy is more than just saying distance between consecutive terms is small. It says distance between any 2 terms is small, whether they're consecutive or not, any 2 terms past a certain point. Also, the distance between consecutive terms being small doesn't actually mean that the sequence is bounded. Yeah. So here's an example. This is going to rely a little bit on earlier calculus knowledge you might have. If I let, for example, x sub 1 be 1, x sub 2 be 1 plus 1/2, x sub 3 be 1 plus 1/2 plus 1/3, etc. X sub n is just the sum as I goes from 1 to n of 1 over I. What is x sub n plus 1 minus x sub n? Well, it's all fractions, all 1 over something, up to 1 over n plus 1. So 1 plus 1/2 all the way up to 1 over n plus 1. And then what do? I take away everything up to 1 over n, so what remains is 1 over n plus 1. So the distance between two consecutive terms is 1 over n plus 1, which is smaller and smaller, converging to 0. But you might recognize these sums here as partial sums of the harmonic series. The limit of xn is infinity, not converging. Even though the distance between two terms is getting smaller and smaller, the terms themselves are growing to infinity. Cauchy is not just saying the distance between two terms is small. It's saying the distance between any two terms, whether they're consecutive or not, is small, past a certain point. So we have shown that Cauchy sequences are bounded. Now we know, since it's a bounded sequence by Bolzano-Weierstrass, it has a subsequence which converges. So every Cauchy sequence must have a convergent subsequence. It converges to a real number because it was bounded, and therefore I'm going to call that limit L. So here we have a subsequence that converges to L. So if the limit's going to exist, yeah, all subsequences must have the same limit. We did prove that if a sequence has a limit, then every subsequence must have the same limit. And since we just assumed one subsequence has limit L, if the limit exists, its limit had better be L. That's exactly right. So if we're going to prove that the Cauchy sequence has a limit, we're going to prove that its limit is the same L that we just invoked here. So let's prove it. The limit of the original sequence is exactly L. Let epsilon be positive, therefore so is epsilon over 2. We want to show that the distance from xn to L is eventually less than epsilon. But since epsilon over 2 is positive, and the subsequence x sub a sub n converges to it, there is a cutoff point past which the terms of that subsequence are within epsilon over 2 of L. But the original sequence is Cauchy, so past a certain point, any two terms of the sequence are close to each other. So past a certain point, I'm going to have both of these things. Any two terms of the sequence are close to each other within epsilon over 2. But also, if I'm in the special subsequence that Bolzano-Weierstrass gave us, those terms are within epsilon over 2 of L. So in our original sequence, x1, x2, x3, x4, etc. I'm just going to keep writing until we have sufficient terms here. Bolzano-Weierstrass gives us a subsequence. So this subsequence is converging to L. If I keep going, past a certain point, the terms of my subsequence are within epsilon over 2 of L because the subsequence is converging to L. However, the sequence was also Cauchy, so past a certain point, any two terms are within epsilon over 2 of each other because the sequence is Cauchy. So if I go past the larger of the two, whichever of these two cutoff points was bigger, my subsequence is close to L. My original sequence may have lots of other terms, but they're all close to one another, which means all of these terms are also close to the terms of the subsequence, because Cauchy says any two terms are close to each other, including the terms of the subsequence. And if the subsequence is epsilon over 2 away from L, and every term of the sequence is within epsilon over 2 of the subsequence, well then, which of our geometric named inequalities is going to come into play, do you think? So yes, any term compared to L, I just do this intermediate step of comparing it to one of the terms of our subsequence. But by the triangle inequality, I can split it up like this. According to the fact that the sequence was Cauchy, the first term is small, and because the subsequence was converging to L, the second term is small. And there they are. Any term of the subsequence past a certain point is within epsilon of L, therefore it's converging to L overall. In conclusion, we showed if a sequence converges to a real number L, it must be Cauchy, but we also showed if a sequence is Cauchy, it must converge to a real number L. The two definitions are logically equivalent. For an explicit sequence, like a list of numbers you're staring at, the distinction between the two is not always so helpful. There's going to be other limits, other techniques we learn for computing limits and finding them, and then just proving that the limit is L directly. Things like L'Hopital's rule. Okay, once you have a way of computing what the limit should be, then you can just prove it using that number L. So why do we care about this Cauchy definition that's a little squishier? Well, there are going to be points later on where the sequence we need to show converges isn't an explicit thing in front of us. So instead of a sequence being something like x sub n is given by a formula, 2n plus 1 over 1 minus 3n, maybe x sub n is abstractly defined as something like the supremum of all Riemann sums of a function f of x on a particular interval where partitions are restricted to be of a certain norm. And this all sounds like word salad, but it is all stuff we're going to learn, okay? Point being, the sequence might be very abstractly defined, and then having a specific limit and trying to show it goes to this number, 0.872, is not going to be practical. However, if we can show it's a Cauchy sequence, because then we can compare one abstractly defined thing against another abstractly defined thing, remember we're comparing terms of the sequence to each other, that might actually be easier sometimes if you don't have an explicit formula or explicit numbers to work with. Yeah, which might sound frustrating, especially if you're a bit of an intuitionist and you want this sort of stuff to make sense and you want it to have something that has nice mental meaning to you. But hey, we're going to do it anyway, sorry. So that'll conclude our work with Cauchy sequences. Hopefully you learned some stuff. Come on back next time. We're going to move on to the study of functions.